As many others, I became interested in physics by reading too much science fiction. Teleportation, levitation, wormholes, time travel, warp drives, and all that I thought was super fascinating. But of course, the depressing part of science fiction is that it's not real. So, to some extent, I became a physicist to find out which science fiction technologies have a chance to one day become real technologies. Today, I want to talk about warp drives because I think on the spectrum from fiction to science, warp drives are on the more scientific end. And just a few weeks ago, a new paper appeared about warp drives that puts the idea on a much more solid basis. But first of all, what is a warp drive? In the science fiction literature, a warp drive is a technology that allows you to travel faster than the speed of light or superluminally by warping or deforming space-time. The idea is that by warping space-time, you can beat the speed of light barrier. This is not entirely crazy for the following reason. Einstein's theory of general relativity says you cannot accelerate objects from below to above the speed of light because that would take an infinite amount of energy. However, this restriction applies to objects in space-time, not to space-time itself. Space-time can bend, expand, or warp at any speed. Indeed, physicists think that the universe expanded faster than the speed of light in its very early phase. General relativity does not forbid this. There are 2 points I want to highlight here. First, it is a really common misunderstanding, but Einstein's theories of special and general relativity do not forbid faster-than-light motion. You can very well have objects in these theories that move faster than the speed of light. Neither does this faster-than-light travel necessarily lead to causality paradoxes. I explained this in an earlier video. Instead, the problem is that, according to Einstein, you cannot accelerate from below to above the speed of light. So the problem is really crossing the speed of light barrier, not being above it. The second point I want to emphasize is that the term warp drive refers to a propulsion system that relies on the warping of space-time, but just because you are using a warp drive does not mean you have to go faster than light. You can also have slower than light warp drives. I know that sounds somewhat disappointing, but I think it would be pretty cool to move around by warping space-time at any speed. Warp drives were a fairly vague idea until in 1994, Miguel Alcubierre found a way to make them work in general relativity. His idea is now called the Alcubierre Drive. The explanation that you usually get for how the Alcubierre Drive works is that you contract space-time in front of you and expand it behind you, which moves you forward. That didn't make sense to you? Just among us, it never made sense to me either, because why would this allow you to break the speed of light barrier? Indeed, if you look at Alcubierre's mathematics, it does not explain how this is supposed to work. Instead, his equations say that this warp drive requires large amounts of negative energy. This is bad. It's bad because, well, there isn't any such thing as negative energy. And even if you had this negative energy, that would not explain how you break the speed of light barrier. So how does it work? A few weeks ago, someone sent me a paper that beautifully sorts out the confusion surrounding warp drives. To understand my problem with the Alcubierre drive, I have to tell you briefly how general relativity works. General relativity works by solving Einstein's field equations. Here they are. I know this looks somewhat intimidating, but the overall structure is fairly easy to understand. It helps if you try to ignore all these small Greek indices, because they really just say that there is an equation for each combination of directions in space-time. More important is that on the left side you have these r's. The r's quantify the curvature of space-time. And on the right side you have t. T is called the stress-energy-tensor, and it collects all kinds of energy densities and mass densities. That includes pressure and momentum flux and so on. Einstein's equations then tell you that the distribution of different types of energy determines the curvature, and the curvature in return determines how the distribution of the stress energy changes. The way you normally solve these equations is to use a distribution of energies and masses at some initial time. Then you can calculate what the curvature is at an initial time, and you can calculate how the energies and masses will move around and how the curvature changes with that. So this is what physicists usually mean by a solution of general relativity. It is a solution for a distribution of mass and energy. But you can instead just take any space-time, put it into the left side of Einstein's equations, and then the equations will tell you what the distribution of mass and energy would have to be to create this space-time. On a purely technical level, these spacetimes will then indeed be solutions to the equations for whatever is the stress-energy tensor you get. The problem is that, in this case, the energy distribution which is required to get a particular spacetime is in general entirely unphysical. And that's the problem with the Alcubierre Drive. It is a solution to general relativity, but in and by itself, this is a completely meaningless statement. Any spacetime will solve the equations of general relativity, provided you assume that you have a suitable distribution of masses and energies to create it. The real question is therefore not whether a spacetime solves Einstein's equations, but whether the distribution of mass and energy required to make it a solution to the equations is physically reasonable. And for the Alcubierre Drive, the answer is multiple no's. First, as I already said, it requires negative energy. Second, it requires a huge amount of that. Third, the energy is not conserved. Instead, what you actually do when you write down the Alcubierre spacetime is that you just assume you have something that accelerates it beyond the speed of light barrier. That it's beyond the barrier is why you need negative energies, and that it accelerates is why you need to feed energy into the system. Please check the info below the video for a technical comment about just what I mean by energy conservation here. Let me then get to the new paper. The new paper is titled Introducing Physical Warp Drives, and it was written by Alexei Bobrik and Gianni Martire. I have to warn you that this paper has not yet been peer-reviewed, but I've read it and I'm pretty confident it will make it through peer review. In this paper, Bobrik and Martire describe the geometry of a general warp drive spacetime. The warp drive geometry is basically a bubble. It has an inside region, which they call the passenger area. In the passenger area, spacetime is flat, so there are no gravitational forces. Then the warp drive has a wall of some sort of material that surrounds the passenger area. And then it has an outside region. This outside region has the gravitational field of the warp drive itself, but the gravitational field falls off, and in the far distance one has normal flat spacetime. This is important so you can embed the solution into our actual universe. What makes this fairly general construction a warp drive is that the passage of time inside of the passenger area can be different from that outside of it. That's what you need if you have normal objects like your warp drive passengers and want to move them faster than the speed of light. You cannot break the speed of light barrier for the passengers themselves relative to space-time. So instead, you keep them moving normally in the bubble, but then you move the bubble itself superluminally. As I explained earlier, the relevant question is then, what does the wall of the passenger area have to be made of? Is this a physically possible distribution of mass and energy? Bobrik and Martire explain that if you want superluminal motion, you need negative energy densities. If you want acceleration, you need to feed energy and momentum into the system. And the only reason the Alcubierre Drive moves faster than the speed of light is that one simply assumed it does. Suddenly it all makes sense. I really like this new paper because to me it has really demystified warp drives. Now, you may find this somewhat of a downer because really it says that we still don't know how to accelerate to superluminal speeds. But I think this is a big step forward because now we have a much better mathematical basis to study warp drives. For example, once you know how the warped spacetime looks like, the question comes down to how much energy do you need to achieve a certain acceleration. Bobrick and Martoyer show that for the Alcubierre Drive, you can decrease the amount of energy by seating passengers next to each other instead of behind each other, because the amount of energy required depends on the shape of the bubble. The flatter it is in the direction of travel, the less energy you need. For other warp drives, other geometries may work better. This is the kind of question you can really only address if you have the mathematics in place. Another reason I find this exciting is that while it may look now like you can't do superluminal warp drives, this is only correct if general relativity is correct. And maybe it is not. Astrophysicists have introduced dark matter and dark energy to explain what they observe. But it is also possible that general relativity is ultimately not the correct theory for spacetime. What does this mean for warp drives? We don't know, but now we have the mathematics to study this question. So I think this is a really neat paper, but it also shows that research is a double-edged sword. Sometimes, if you look closer at a really exciting idea, it turns out to be not so exciting, and maybe you'd rather not have known. But I think the only way to make progress is to not be afraid of learning more. Thanks for watching. See you next week.